Here's a proof for Euler's identity, our Euler's formula. This proof doesn't take any knowledge of the Maclaurin series of sine, cosine, or e, and it doesn't require knowing the derivative either. It just takes a basic understanding of limits, complex numbers, and de Moivre's theorem. Let's first start off with the definition of e, which is 1 plus 1 over n to the nth power as n approaches infinity. With that, we can take this to the x power, which can be simplified down to 1 plus 1 over n to the nxth power for the definition of e to the x. Now we can multiply the 1 over n inside the parentheses by x over x to get x over n times x. After that, we can make a substitution that n times x equals omega, which will make things much simpler. We can also substitute I times theta for x to get what e to the I theta will look like. Let's look at that theta over omega term for a bit. So we know that n is approaching infinity, so we can include that omega is also approaching infinity, and its reciprocal, 1 over omega, would approach 0, since it's getting infinitely smaller, which is why we can also take the limit as 1 over omega approaches 0. By the way, if there's anything wrong with my notation, let me know in the comments. I really don't know how to use this type of notation. I think typically the 3 dots are meant for proofs, and an arrow will work better, but this gets the job done. Now let's look at what happens as sine and cosine approach 0. Here we have the graphs for cosine of alpha and sine of alpha from 0 to 2 pi, where alpha is an angle in radians. If we see what happens as alpha approaches 0, then we can see that sine of alpha equals 0 and cosine of alpha equals 1. Going back to our original equation, we can substitute the terms inside of the parentheses for cosine and sine, because cosine of 0 is 1 and sine of 0 is 0. We're almost there, but we can simplify this down further using de Moivre's theorem, which states that any complex number z that is expressed in its polar form with sine and cosine taken to the nth power is the same as its radius to the nth power times cosine of n theta plus I sine n theta. Going back to our equation, we can then use de Moivre's theorem to bring the omega into the cosine and sine to get the angle as omega times theta over omega. Since the radius is 1 for this complex number, we don't need to account for that, and the omegas then cancel out to be left with the nice formula that e to the I theta equals cosine theta plus I sine theta. We can then substitute pi for theta to get e to the I pi equals cosine pi plus I sine pi. Cosine pi is -1 and sine of pi is 0, which cancels out the I term. Moving things around, we get our answer, e to the I pi plus 1 equals 0. I hope you enjoyed that one. It's my first time doing a Manon project like this, and I didn't really know what I was doing. My source code was really messy, but if you want to see it, I posted everything on my GitHub. Just don't roast my abysmal code.